So some people ask if we could go over some properties of intervals. I think that's a fine idea. We'll talk about that for a little bit here. I'll point out that a lot of them are rules that we kind of use just without even thinking about them. And actually, I'll start there. So here are a couple rules that I feel like we use all the time. So here are some properties of intervals. And I guess I'll write them in the same order that one of the teachers has written them, just because it's probably in order that they're written in the textbook. So we might as well be consistent. So the first one is that for a definite interval, the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. I would say this rule actually doesn't come up that much in usage personally, unless someone's particularly trying to make you use it. So for example, someone could say something like, well, given that the integral from 1 to 3 of f of x dx is equal to 2, and f of x is, sure, let's say f of x is, think about this for a second. So I'm like, now I'm like, how do I want to do this? Sure. F of x is odd. I want to find I probably actually don't need the property I'm about to use here, but we'll do it anyway. Find the integral from -1 to 3 of f of x dx. I might be using a different property. This question is not a good question for the example I just did. I just made it up and I was like, oh, that's not exactly what I'm thinking about, but it's still a good question. It makes us think. It's not what I wanted to say. So I'm actually going to use some other properties. So we'll come back to this. We're going to come back. Sorry, I know. We're going to come back. You're waiting. Let's look at some other properties. Second property, which also maybe doesn't come up all that often, which is that if you do the definite integral from a to a of a function, you're going to get 0. That's it, right? If you're finding the area under your function f of x and you're starting at a and you're ending at a, you're not getting anything. Okay, let's get closer to the ones that we might actually feel like we use more often. The integral from a to b of k times f of x, where k is a constant, you can pull that constant out, and we do all the time, kind of without thinking about it. In the second, we're going to combine that with this other property that we have, which is that when you find the integral from a to b of f of x plus g of x, we can break this up into the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And this property, which I'm going to modify or add to in just a second, combined with property 3, I think is one we use all the time. So here's an example of how we use this without using it. I'm going to do a definite and an indefinite one. So let's say I wanted to find the integral of 3x squared plus cosine of x minus e to the x dx, minus 4 e to the x dx. I'm going to use these two properties without actually saying them. So here's my answer. My answer is going to be, well, the antiderivative of 3x squared is 3x cubed over 3. The antiderivative of cosine of x is sine of x. And the antiderivative of 4 e to the x is 4 e to the x, plus a constant. But here's the work we really did using those properties that we didn't actually state or need to state at the point. Nobody expects you to write what I'm about to write. But we could have, if we really wanted to, written this integral as the integral of 3x squared dx plus the integral of cosine of x dx minus the integral of 4 e to the x dx. And then we could have pulled out the constants as well and written it as 3 times the integral of x squared dx plus the integral of cosine of x dx minus 4 times the integral of e to the x dx. No one wants you to write that work. You shouldn't write that work unless you were specifically being asked to show those steps. And then we would get exactly what we got here. 3 times x cubed over 3 plus the antiderivative sine, cosine is sine, minus 4 times the antiderivative of e to the x is e to the x. And then we slap on a constant. And yes, we should simplify 3x cubed over 3 is just x cubed, but we've got. So these two properties we use all the time. And additionally, we usually write this fourth one here as the integral of f of x plus or minus g of x is equal to the integral of f of x plus or minus the integral of g of x. A few more things. Then I promise we're gonna come back to that problem I mentioned earlier. Just it's waiting in the wings for us. So a couple more properties. One that we did mention last class. I know I've mentioned it before. That the integral from a to b of f of x dx can be written as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And actually, here's an example of where you could use that first property I talked about to say a few things. So I'll point out that at least in Arlac's class, she says that C should be between A and B. And while I like to think of it that way, it's actually not necessarily true. C does not have to be between A and B. It does need to be in the domain of the function, but technically it's perfectly fine to say if you're taking the area under the curve f of x from A to B, you can break that area up at any point C, whether it's in between. Say, great, here's my integral from A to C of f of x in red. Can I see the colors right? Yeah, you can see that. And here's, I'm gonna squeeze that in there, the integral from C to B of f of x in green. And those definitely add up to the total area under the curve from A to B. So someone could ask a question like, and I'm gonna make sure this one actually makes sense here. Given that we have the integral from 1 to 17 of f of x dx is equal to 4, and the integral from 1 to 20 of f of x dx is equal to 13, find the integral from 17 to 20 of 3 times f of x dx. 3 is not a good choice there. Let's make that a 5. It's not a bad choice. There's just reasons I don't want it to be a 3. So how am I thinking about this? Well, there's a couple ways to do it. I'm really thinking about the following. I know that the integral from 1 to 17 of f of x plus the integral from 17 to 20 of f of x should equal the integral from 1 to 20 of f of x. That's what I'm thinking of when I see these different intervals. I've got 1 to 20, I've got 1 to 17, I've got 17 to 20, and how can I relate them? So then I know what a few things are. I know what this is. I know that's 13. I know what this is. I know that's 4. So if I want to find this, and I'll do 5 times in a second, I can say that the integral from 17 to 20 of f of x dx, okay, it's going to equal this integral minus that integral. And for the sake of the problem, we should just plug in the values and get 13 minus 4, which is going to be 9. So then the thing I'm actually looking for, which is the integral of 5 times f of x from 17 to 20, well, that's going to be equal to 5 times the integral from 17 to 20 of f of x, right? Using one of those properties, and I'm going to get 5 times 9, which is 45. But I also want to point out, because it seems very opportune to do so, look how I could rewrite this. I could rewrite this as the integral from 1 to 20 of f of x. And now I'm going to change the order of my limits of integration here and change the sign there. So I'm going to say that's going to be plus the integral from 17 to 1 of f of x dx. It's not wrong. It's totally allowed. It just looks weird. And then if you really want, I think I can squeeze this in here. We can say that the integral from 17 to 20 of f of x dx, I'm just going to reorder these and write it as the integral from 17 to 1 of f of x plus the integral from 1 to 20. So technically, if you have an integral from some a to b, 17 to 20, you can break it up anywhere between 17 and 20 or not. So here I'm thinking of breaking it up at 1. I'm just going from 17 to 1 and then from 1 to 20. It's kind of funky, but it works. I think it's kind of cool. Okay. As usual, I should just point out, if you have questions, you can ask them. Say words, raise your hand. If you're in the Zoom, you can certainly say words or write something in the chat. I should have the chat open somewhere here. One second. Just to make sure I'm not missing anything in the chat. Where is the chat? Okay, there it is. Good. All right. So, yeah.
Where did the
I made it up. So I just said I wanted the question to be slightly more challenging. So instead of just finding the integral from 17 to 20 of f of x, I slapped in a 5 and said, oh, we know we're gonna have to use property number 3. This is the integral of a constant times a function is just the constant times the integral. I just pulled it up front and then said, oh yeah, I know this is gonna be 9. Yeah, just making it. Let's look at the last couple properties here. So this one's written, I like what this one's written. So your teacher has written the following, property 6. I think I have a question for this one as well. So the minimum of x on your interval from a to b of your function. So the minimum value of your function times b minus a is less than or equal to the integral from a to b of f of x is less than or equal to the sure, you could write it as an integral. I was going to save that for a second though. Is less than or equal to the maximum value of f of x over that interval from a to b times b minus a. I think this is kind of more than we really need to write personally. Let's draw a picture. So let's say, and actually let's just not just draw a picture. Let's pick a nice example here. I had an example. Sure. Yeah. So let's say our function, okay, yeah, that'll be fine. Let's say our function is the square root of 9 plus 7 times tangent of x. Yeah, that looks terrible. Probably not something I'm able to anti-differentiate. It's probably actually impossible. Likely anyway. And our interval is going to be 0 to pi over 4. If I tried to graph this, well, I know a few things. I know that if I plug in 0, f of 0 is the square root of 9 plus 7 times tangent of 0 is just 0, because tangent of 0 is 0. Square root of 9 is 3. Similarly, f of pi over 4 is going to be the square root of 9 plus tangent of pi over 4 is 1. So 7 times 1 is 7, and that square root of 9 plus 7 is 4. So on this interval from 0 to pi over 4, the function starts at a low value of 3 and ends at a high value of 4. And I don't exactly know what it looks like. Maybe it looks something like this. I'm really making it up. But what we know for sure is that the area under this curve is more than the area under this curve. Y equal to 3, the minimum value of the function on the interval. And so certainly the area under the curve is more than the area of this rectangle, which I would probably actually write as, instead of writing as the minimum of f of x over ab times b minus a, I think it's easier just to say it's the integral from 0 to pi over 4 of 3. So the minimum value is 3. And if we integrate that, well, when you integrate a constant, you're finding the area under that constant, but that's just the area of what shape? What shape did I draw? It's a rectangle. And that rectangle has a base of pi over 4 and a height of 3. That's really just going to be 3 times pi over 4 minus 0, which is 3 pi over 4. And the maximum value of f of x over the interval, so I was going to use a different color for it, but too late, times b minus a in this case is just the same as the integral from 0 to pi over 4 of the maximum value, which is just going to be 4 times pi over 4, which is pi over 4 minus 0. So this area under the curve is certainly less than the green region here and more than the red region. Sorry, I wrote the red region, the green region in red, apologies. But this area that I'm actually looking for is between those two. That's all this theorem is saying, is that if you have a function that's bounded above by some number and below by some number, the area under that function is between those two numbers multiplied by the length of the interval. And really, I would say this is a consequence of a different property. So this actually is a specific version of the more general, I don't know, property of inequalities for integrals, which is that if you have some function less than or equal to another function, so if g of x is less than or equal to f of x on the interval from a to b, then it is perfectly valid to say that the integral of g of x on the interval from a to b is less than or equal to the integral from a to b of f of x. Because if this function is always higher than that function, then it's going to have more area underneath it than the lesser function. Okay. So let's take a look here. I like that one. 2 more properties, one of which is more important than the other, I think. So if f of x is an odd function, then it's true the integral from negative a to a of your function f of x is going to equal 0. There are lots of examples of this. Let's look at a couple. Let's say I want to find the integral from negative 2 to 2 of x cubed minus x. X cubed minus x? Sure. Let's do x cubed minus 4x. Make it a little bit less terrible. So I could graph it. In fact, I'm going to graph it. So x cubed minus 4x, it has intercepts at 2 and at 0 and at negative 2. How do I know that? Well, if we actually write it out, f of x equal to x cubed minus 4x, if we factor out an x, we're left with an x squared minus 4, and that factors as x times x minus 2 times x plus 2. So we have intercepts at 2, negative 2, and 0. And the function looks, well, if I plug in 1 minus 4 is negative 3. Plug in negative 1 plus 4 is positive 3. So the function looks vaguely like this. Again, my graphs are, never meant to be perfect. It looks something like that. So I want to find the area, I should say the definite integral from negative 2 to 2, which means the net area under the curve that's above the x-axis. Well, all of this area here is getting counted as positive, and all of this area under the x-axis is getting counted as negative. And if you believe my drawing has the symmetry it's supposed to have, those areas are canceling each other out. So we're definitely getting 0 here. And here we can do the work, right? You could actually do the integral and say, well, that's going to be x to the 4th over 4 minus 4x squared over 2 from negative 2 to 2. If I plug in 2, I'm going to get 16 over 4 minus 4 times 4 is 16 over 2. Minus, if I plug in negative 2 to the 4th power is still positive 16. And negative 2 squared is still positive 4, and 4 times 4 is still 16. So we can see that things are definitely going to cancel out. 16/4 minus 16/4 is 0. And negative 16/2 minus negative 16/2 is also 0. But then we can use this idea for functions that are impossible to anti-differentiate. For example, someone could ask us to, someone probably will ask you on an exam to calculate some definite integral like this. Negative 3 pi to 3 pi of x times tangent of x over, not x, x squared, over 1 plus x to the 6th. And the clue that we should be doing what we just did is the fact that our limits of integration are opposites of each other. One's positive something, one's the same negative something. So I'm pretty sure this is 0. And if I asked a question like this on an exam, I would expect students to tell me it's 0 because the function is odd. This equals 0 because f of x equal to x squared times tangent of x over 1 plus x to the 6th is odd. But we should probably also actually show that it's odd. What does it even mean to be odd? Well, visually, it means we have this kind of symmetry, which we call either rotational symmetry or symmetry about the origin, where if you took the graph and rotated it 180 degrees, it would look the same as it did originally. Or alternatively, you can think of reflecting it in both the y-axis and the x-axis, and it would still look the same. If you, I used to bring like a clear piece of paper, I could like flip it over and flip it over. Like, let's see, can you see through this kind of? You can kind of see through that, right? So if I flip it over and then flip it over, it looks the same, but not exactly, right? Yeah, that's kind of cool. That works. I like that. Okay. So that's what these visually this rotational symmetry or symmetry about the origin means. But how do we actually show it? Well, looking here, what I can kind of see is that f of 1 is equal to -3 and f of -1 is equal to +3. More generally, the way we show something's odd is we show that f of -x is equal to negative f of x. That's how we show a function's odd. But you can't just do it for one value. You have to do it for every x value. So we have to show that f of -x is equal to negative f of x. And it's really, really vital that we know which trig functions are odd and which trig functions are even. So every trig function on its own is either odd or even. So think about the graphs of things for a second. Can anyone tell me one of the ones that's even? One of the trig functions that's even. Sorry, I didn't even say what even was, but you might know already. So that is an even function, but I'm looking for a trig function that's even. So I should say, before I ask it again, so you have a great example, and actually, yeah. So y equal to the absolute value of x is an even function. It has the right kind of symmetry to be even, which is just being symmetric about the y-axis, meaning if you just flip this graph across the y-axis, it will look the same as it did. So what's a trig function that has that visual property? It's definitely cosine. So f of x equal to cosine of x is even. And similarly, its reciprocal function also must be even. It's got the same sort of periodicity. So f of x equal to cosine x is even, and f of x equal to secant of x. The reciprocal of cosine is even. And what that means is, we haven't talked about evenness yet. We'll get there in a second. But we'll come back to the even ones, I promise. Whereas the odd ones are the other form. So sine of x is odd. So f of x equal to sine of x is odd. And what that means for us is that sine of negative x is equal to negative sine of x. If you really, really wanted to, you could show that with the trig identity using the angle sum identity. And we can if someone wants me to, but we don't have to. Similarly, tangent of x is also odd. Again, think about the graph of tangent. It's got kind of that, not kind of, it has exactly that rotational symmetry. If you take the tangent graph, in fact, let's take a look. Ooh, okay, sure, that's fine. Let me just show you all, because I can do it with the Desmos, maybe. So, right, if you look at tangent, let's look at sine first. That graph, if you rotate it 180 degrees about the origin, is going to look exactly the same as it did. Similarly, although I know it's kind of funky, tangent also. If you rotate that graph 180 degrees around the origin, all the, like that middle part does rotate back around to be that same middle part. And every other thing, like this, right, this one here rotates around to be that one over there. And you keep going further out, they rotate around to be the other thing. It's kind of neat. In fact, I can't. I wish I could just like turn it upside down, but I don't think there's a way to do that easily on my computer. Curious if there is though, but I don't want to spend time doing that, so we'll figure it out later. What that means for us is that tangent of negative x is equal to negative tangent of x. And if you're not convinced, just think of a couple values. Tangent of negative pi over 3 is in quadrant 4, where tangent's negative, that's equal to negative root 3. Negative tangent of pi over 3, well, tangent of pi over 3 is in quadrant 1. Tangent of pi over 3 is positive root 3, so we get negative root 3. Oh, they're the same. And it is true that tangent of negative x equals negative tangent of x. And the reason I point this out is because to show that this whole thing, that this function is odd, you really need to know that tangent itself is odd. So then we're going to look at f of negative x and see what happens. So f of negative x is negative x quantity squared times tangent of negative x divided by 1 plus negative x to the 6th. A negative thing squared, well, negative x times negative x is positive x squared. We just said that tangent of negative x is equal to negative tangent of x. And negative x to the 6th is positive x to the 6th. Because again, negative x times 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 negative x is positive, because you've multiplied a negative thing an even number of times. And then that's equal to negative x squared times tangent of x over 1 plus x to the 6th. Or you could write down that negative f of x is equal to negative 1 times x squared times tangent of x over 1 plus x to the 6th. Those are the same. I want to emphasize for a second here that if I have negative 1 times a fraction, it's either negative 1 times the top or negative 1 times the bottom, but not both. So you multiply the negative 1 by the top and the bottom, you're really multiplying by negative 1 over negative 1, which is like multiplying by positive 1. So be careful there, right? If you multiply a fraction by negative 1, you can pick which part you want to multiply by, but not both. So that shows the function's odd, which then shows that this integral is in fact equal to 0. And I would definitely ask a question like that on an exam, if it were me giving the exam. But it's not me, so maybe you won't. The other property, which I think is less often used, but is still useful, is the property that, I think I had to, question, yeah. That would also work. Yeah, I like that. Good. So if we did, let me do a different problem. Let's say we did the integral from 2 to negative 2 of x to the 4th times sine of x dx. I could still use the same property. As long as these are opposites of each other, doesn't matter, because we could use that first property. We could use that first property and rewrite this as the negative of the integral from negative 2 to 2 of x to the 4th sine of x dx. And then we can show that our function, I'm going to call it g of x this time, g of x equal to x to the 4th times sine of x is indeed odd, because we can see that g of negative x is equal to negative x to the 4th times sine of negative x. Negative x raised to an even power is going to be positive x to that even power. and sine of negative x is equal to negative sine of x. And that is negative x to the fourth times sine of x, which is negative g of x. And that shows that the integrand is an odd function. So the integral from -2 to 2 of that odd function has to be -0, but -0 is just 0. So yeah, you can totally have them in the opposite order and it still works just fine. The less exciting, but still useful property for even functions is that if you have the integral from -a to, and this is probably, I think it's 9. It's okay. I like to sometimes try to number things appropriately. Yeah, 9. Is that the integral from -a to a of an even function is equal to 2 times the integral from 0 to a of the same even function, if f of x is even. This really is just useful in making things easier to calculate if you're actually doing a definite integral. Oftentimes, if you look at like the answers in the back of a textbook, you will see them jump from something to 2 times your integral and the limits of integration will change. That's the property they're using. So for example, if I wanted to find, say, the integral from -3 to 3 of 9 minus x squared, well, I'll point out this is representing the area under the curve y equals 9 minus x squared from -3 to 3. If I plug in 3, I do get 0. If I plug in -3, I do get 0. If I plug in 0, I do get 9. It's a downward opening parabola. It's kind of like that. I'm trying to find all the area under that curve. But instead of finding the area under that curve, since this function is even, which I know again I haven't defined what an even function is, we'll get there. That's equal to 2 times the area under the curve from 0 to 3 of the same function. So instead of finding all the area under the curve, what I'm really doing is finding the area under this half and then just multiplying it by 2. It's really a property of convenience. It's not super duper important, I would say. Like of all the properties I mentioned, it's probably the least important of them. But if we did this, we'd end up getting 2 times, let's see, the antiderivative of 9 is 9x. The antiderivative of x squared is x cubed over 3. We're going from 0 to 3. So we end up getting 2 times 9 times 3 minus 3 cubed over 3. Minus, if I plug in 0, I will get 0 minus 0. So I'm not going to write it down. But again, we should always be thinking about being sure that if you plug in 0, you actually do get zeros there. So here we end up getting 2 times 27 minus 27 over 3 is 9. So we get 2 times 18, which is 36. Just to kind of backtrack a hot minute here. So to show f of x is even, we have to show that basically you get the same y value whether you plug in a positive x value or the corresponding negative x value. So we have to show that f of negative x is equal to f of x. And really, we don't typically do this. Like if you're using this property, you're using it because you know the function is even. You're not trying to conclude something like, oh, the interval is 0 because the function's odd, and I really need to show the function's odd. You're just using like, yeah, I know this thing's even, so I'm just going to use it. But to show this is even, we would say f of negative x is 9 minus negative x squared, which is just 9 minus x squared, which is the original function. And there are lots of kind of interesting, weird rules for even and odd functions, which aren't really super important to know. But you could imagine them as being true based on polynomials. So I'll point out that any polynomial that has all even powers is even. So for example, f of x equal to 3x squared plus 4x to the 4th plus 9x to the 100th power is even. And any polynomial with just odd powers, x cubed plus 7x to the 5th, is odd. And then if you multiply them together, weird things would happen. But if you multiply them together, I think all the powers would end up being odd, which means it would be odd. So an odd times an even would be an odd function. And an even times an even would be an even function. And an odd times an odd would be an even function. So you can kind of use very basic examples of odd and even functions, like maybe even more easily x squared and x cubed, and see what happens when you multiply or add them together. And interesting things happen. But I don't want to get too into that because it's not really that important. Okay, so back to the question I asked way at the beginning, which I know some of you are like, he asked the question, and you might have forgotten about it. I didn't forget about it. So here's what we were given. We were given that the integral from 1 to 3 of f of x dx is equal to 2, and f of x is odd. And then I said we want to find, I want to find the integral from -1 to 3 of f of x dx. Which I think is actually not a terrible, it's kind of a maybe thought-provoking question. I don't know. I think it makes you think a little bit. So we're given that this thing is odd, but we're given that limits of integration are not particularly useful, right? If it's an odd function, the only thing that's really helpful to me is from going from like -2 to 2, -1 to 1, or -3 to 3. So what I could do here is break this up. I could break it up as the integral from -1 to 1 plus the integral from 1 to 3. But then what's this first part have to be equal to? Yeah, it has to be 0 because it's an odd function and the limits of integration are opposite values. And then this other part here, they told us that part was 2. So we got 2. Seems all right. Maybe not the best question. Okay. There was something else that was on my mind. Oh yeah, let's look at this. Let's look at a few of these. So just to go a little bit further down this. Let's say we have the file. Oh, that's interesting. There's my schedule for some reason in the middle of things. Okay. Let's do this. Let's say we are given the following. F of x is odd. G of x is even. And we're also told the following integrals. The integral from 0 to 4 of f of x dx is equal to 3. The integral from 0 to 6 of f of x dx is equal to 10. The integral from 0 to 4 of g of x dx is equal to -5. And the integral from -4 to -7, which you might think of as being out of order, which technically it is. It's okay though, it's totally allowed. That interval is 8. Now we're going to find a few things. So we're going to find first the integral from 4 to 6 of f of x. All right, so there's a couple ways you can think about it. The way I'm going to imagine it is by drawing a picture. I think these kind of problems are really, it's good to draw a picture. So if I'm trying to find the area under the curve between 4 and 6, I want that, but I know that the integral from 0 to 4 of f of x is 3. I know that the total area is 10. So then how much does the little shaded part over here have to be? What's 10 minus 3? It's got to be 7. Now, the work I'm going to write is that I can either write one of two things. I would like to think of this as the integral from 0 to 6 minus the integral from 0 to 4 of f of x. That seems like the most natural way of imagining this, I think. And then that's just going to be exactly what we said it was. It's going to be 10 minus 3, which is 7. But if you really like, you could think of, well, James, I know you said the thing before. You said you could break the integral from 4 to 6 up wherever you like. I'm going to break it up at 0. So watch this. We could instead say that this is equal to the integral from 4 to 0, thinking of 0 as being the quote unquote middle, and then the integral from 0 to 6. But then the integral from 0 to 4, we have to, sorry, I said that wrong. The integral from 4 to 0, we need to change the order of integration so that we have something that we actually know, which is that the integral from 0 to 4 is equal to 3. So we can rewrite this as the negative of the integral from 0 to 4 plus the integral from 0 to 6. That's going to equal -3 plus +10, which is still 7. So you can kind of get there either way. It's kind of neat. I think it's kind of neat that you can do it either way. I see some disbelieving looks, I would say, which is fine. I can see being suspicious of this. It feels kind of weird, but it does work. Let's look at a few more questions here, and I guess I will keep that up there. So let's say we wanted to find, I like that question too. I feel like this next question is actually very much the same. If I wanted to find the integral from -4 to 6 of f of x, I feel like this is very similar to the question I just asked. I'm going to break this up into the thing I just did and the rest. So we can break this up as the integral from -4 to 4. Why would I do that? Sorry, I should do the rest. Why would I do that? How is that helpful to me? What's that part equal to? 0. Why is it 0? What do we know about f of x? It's equal to 0 because f of x is odd. So this is actually the same as the one we just did. This is going to be 0 plus that integral, which from part A was what, 7? Yeah, 7. All right, why don't you all try this one? By finding the integral from 0 to 7 of g of x. You will not need to use the property that g of x is even here. That might be a lie. I could be a big liar. You might need to use the property. So yeah, here's what I'll give you as well. I would point out that since the integral from -4 to -7 of g of x is equal to 8, it is also true that the integral from -4 to -7. Yeah, that's interesting. Okay. From 7 to 4 of g of x dx is also equal to 8. That seems kind of weird, right? Here's what we're thinking of graphically. So -7, -4. But if you're going the opposite direction, what I should really maybe say here, which might make this easier to see, is that the integral from -7 to -4 of g of x is actually equal to -8. So going from left to right, the area under the curve below the above the x-axis is, sorry, the area that is under the curve that's above the x-axis is -8. Or a better way of saying that is that the area below the x-axis is -8. So you've got some sort of thing here where that area is -8. And so then over here, we have the symmetry of that. We have that this area also looks like -8, which means that you could say that the integral from 4 to 7 is -8, or that the integral of 7 to 4 is +8. Kind of weird. Let me pause for a second. Questions about this? Why does this work this way? Well, it's because of the evenness of G. So I think it's maybe easier to see. And yeah, if you need to go, you're free to go whenever you need to go always. So I think it's easier to see that, oh yeah, if the integral from 4 to 7 is -8, the integral from -7 to -4 is also -8. Because we still have to do this left to right. So I'm trying to find this. I'm trying to write it in terms of what I got. I've got these things here. I'm probably going to try and break it up at 4 because I don't see another way. So I'm going to write this as the integral from 0 to 4 of g of x plus the integral from 4 to 7 of g of x. And then we're given this. This is equal to -5. You can't see what I'm pointing to. Sorry, one sec. Sorry. The integral from 0 to 4 of g of x is equal to -5. And this is equal to, it looks like, -8 because of all of the stuff we wrote over here. Yeah. Not my favorite, but not terrible. Not unreasonable to ask. Someone could ask a question like this. It is not out of our wheelhouse for sure. Yeah, I think that's enough with that. Let's go ahead and talk about this question. Oh, there you go. Come on, for a second. There are always things in the way. So let's continue talking about definite intervals. There's a few things I want to look at. Someone asked me specifically this question, which I think is worthwhile. So they said we want to find the definite integral from 0 to 1 over root 3 of 1 over 1 plus 4x squared, which is a little challenging. To me, this looks like the antiderivative is what kind of function? What is this maybe looking reminiscent of? Not natural log, although that's not a terrible guess. There's a word, there's a prefix you're missing, but yes, arctangent. So this function looks similar to the derivative of arctangent. We know that the derivative of the arctangent of x is 1 over 1 plus x squared. This one is 1 over 1 plus 4x squared. And I really, there's probably a formula to memorize for this. I don't remember what it is. So what I would do instead is I want to try and make this look like 1 over 1 plus u squared. So we're going to do a u sub here, even though you probably could do this without doing a u sub. So we're going to rewrite this as the integral from 0 to 1 over root 3 of 1 over 1 plus, I'm going to write that as 2x squared, so that I can more easily see my candidate for u. So we're going to let u equal 2x. Our du dx is just the derivative of 2x, it's 2, which means our du is equal to 2 times dx, and that 1/2 times du is equal to dx. So then we're going to start replacing things. I'm going to say this every time for a while. Whenever you're doing a u sub, always want to make sure that dx turns into whatever thing with du it needs to be. In this case, we've isolated dx, so it's really easy to replace dx with 1/2 times du. So we're going to rewrite this as the integral of, I'm going to leave off the limits of integration for now. Dx first. Dx becomes 1/2 times du. Please, when you do this, make sure you turn dx into du first. Not just by writing du, but by actually replacing dx with whatever it's equal to in terms of du. It'll save you some time, it'll save you some heartache. And then the rest of it, it's going to be 1 over 1 plus, now I can replace the 2x with u. And then I personally think that when we do a definite integral and do a u sub, it's worth our time to change the limits of integration. This one might, no, I don't think so. This one's fine. So we know from our original statement here that our limits of integration are x equals 0 to x equals 1 over root 3. So if x equals 0, u is going to equal 2 times 0, which is still 0. And if x equals 1 over root 3, 1 over root 3, is that what? Yeah, okay. U is going to equal 2 over root 3, which I'm mildly concerned about, but we'll live. Oh, no, that should be fine. So now we can integrate this. I might pull the 1/2 out in front, but it's not super necessary here. So we're going to write this as 1/2 times the antiderivative of 1 over 1 plus u squared is the arc tangent of u. Or if you prefer, the inverse tangent phi. Oh, I forgot to write in limits of integration. Sorry. Those should be limits of integration, which are u equals 0 to u equals 2 over root 3. I will point out, just from a perspective of anti-differentiation, if you actually finish the problem the other way, your antiderivative would be 1/2 arctangent of 2x plus c. But we don't have to do that because we change our limits of integration, so we can just plug in. Which again, I feel real not great about. I feel like this problem was written in a way that they meant for the limits of integration to be nice, and they turned out to be not nice. So plugging in 2 over root 3, I get 1/2 arctangent of 2 over root 3 minus 1/2 arctangent of 0. If you did this instead, and you plugged in these limits of integration, you would get the same thing. If you plugged in 1 over root 3 here, you would get 1/2 arctangent of 2 over root 3 minus 1/2 arctangent of 2 times 0 is 0. And then the only simplifying that we can do here is the fact that arctangent of 0 is equal to 0. The arctangent of 2 over root 3 is not a value that I'm familiar with, nor should we be. If it was arctangent of 1 over root 3, the angle would be pi over 6. Or arctangent of 2 over root 3, oh God, no, you shouldn't do that. No, I'm not even going to say it. We're going to leave it like that. Kind of weird. Let's look at some more definite rules. Let me grab some more definite rules here. Sorry, one second. I've got things all over the place here. Sure. So let's look at a slightly more interesting problem. Let's say we want to find the integral from 1 to 5 of x times the square root of, 1 plus x. Looks kind of terrible. The only thing I can think to do here is to do a u sub. And the only candidate for u really is whatever's inside our function. Not always, but in this case, it certainly is. So we're going to try letting u equal 1 plus x. And our du, our derivative of 1 plus x, well, is 1 times dx. So this one isn't too terrible. I'm going to change my dx to du. And then the square root of 1 plus x, the square root of u. Then what about my leftover x? Well, this is where we're going to do what's called a back substitution, where any leftover variables, we go back and look at our u substitution, and we solve for x. So here we're going to say that x is equal to u minus 1. And we're going to plug that in for x right here. And yeah, I still think it's worthwhile to change the limits of integration. So if x is 1, u is going to be 1 plus 1, which is 2. X is 5, u is going to be 1 plus 5, which is 6. There are occasionally times where it's not the best idea to change your limits of integration when you're doing a definite integral with u substitution, but it is often a good thing to do. So let's go ahead and figure out what's going on here. We've got the integral from 2 to 6. I'm going to distribute the square root of u. U times u to the 1/2 is u to the 3/2. And 1 times u to the 1/2 is u to the 1/2. And now we're going to anti-differentiate. The antiderivative of u to the 3/2 is u to the 5/2 divided by 5/2, or times 2/5. The antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2, or times 2/3, from 2 to 6. These are not nice numbers. It's not going to come out pretty. That happens all the time. So here we're going to plug in. We're going to get 2/5 times 6 to the 5 halves minus 2/3 times 6 to the 3 halves minus 2/5 times 2 to the 5 halves minus 2/3 times, sorry, so that's to be a 6, apologies. No, a 2, sorry, my brain got mixed up here. 2/5 times 2 to the 5 halves minus 2/3 times 2 to the 3 halves. Very unpleasant final answer there. But also not really, right? It's just something we have to write down, but it's really not that terrible. So, oh yeah, there was that. What time is it? Okay, yeah, we got time. Let's do another one, and let's actually look over here. So let's say we want to find, yeah, like you. So we want to find the integral from 0 to, sure, 2 x squared times the square root of x cubed plus 1 dx. And then after we do this, well, after we do this, we'll do something else. So, same idea. In fact, I want you all to do the u sub. So pick your u, rewrite your integral. I believe there's a pretty natural choice for you. Something in the chat. Let's specify, would it be advantageous to simplify the integral? I'm assuming you mean from this previous problem. I don't really see any simplifying the integral that we could do until we get to here. And I definitely feel like I did simplify it by distributing the square root of u. I'm not sure if you could, you can welcome to clarify your question, but I'm not exactly sure if that's what you mean. Let's talk about the first few steps. We're making the choice that u should be the stuff inside the square root. for the typical reasons in that it's stuck inside a function, and importantly, its derivative is showing. The derivative of u with respect to x is 3x squared, meaning our du is 3x squared times dx, or isolating the part that we have, 1/3 times du is equal to x squared times dx. And this is what I really mean when I say that we want to make sure that the dx transforms into the du first. Dx, you need to capture whatever you need or soak up whatever you need with it to make sure that whole x squared times dx gets replaced by just 1/3 times du. So when I start rewriting this, I'm going to rewrite this as, I like to move things around and write this as the square root of x cubed plus 1 times x squared times dx. So that all of this, x squared times dx, is going to get replaced with 1/3 times du. Making sure that that happens first is most important. So then we're going to have the integral of, that's going to be a 1/3 times du at the end. I probably would have written it out in front, but I didn't, so oh well. And then here we're going to have the square root of just u, because x cubed plus 1 is u. And then I, again, am a proponent of changing my limits of integration question. So I saw in my integral that my integral has x squared times dx. So I would love for this right-hand side of this equation to be just what I see in my integral. So what I'm doing is I am saying, oh, I don't really want that 3 there. So I'm multiplying both sides of this equation by 1/3. But then the 1/3 times 3 just becomes 1. So I have an x squared times dx on the right-hand side. Other people, not me, do a different thing. They say, I'm going to solve for dx completely and say that du divided by 3x squared is equal to dx. And then what they do is they take this integral and they write it as x squared times the square root of x cubed plus 1. And they totally just replace dx with du over 3x squared. And then they say that the x squared down here and the x squared up there divide to 1. And then you get the same thing, right? You get your square root of u times your du divided by 3, or your 1/3 times du, depending on how you want to say it. This is a fine way of doing it. It's just not the way I like to do it. Why not? Good question, actually. So there is a reason, and the reason why is because sometimes when you do it this way, the stuff you have below your du doesn't cancel out. And then it becomes much more challenging to figure out what you need to do. And I can think of some examples where it's So yes, but I don't think we're quite there yet, because really a lot of those problems then require integration by parts instead of substitution. So yeah, but that's kind of why I don't like it. So then I would also change my limit to integration, since x was 0 and u is equal to x cubed plus 1. We're going to get u equal to 0 cubed plus 1, which is 1. And x was 2, so u is going to be 2 cubed plus 1, which is equal to 9. Interesting math fact, just because 8 and 9 are the only powers of positive integers that differ by exactly 1. 8 is 2 to the third, 9 is 3 squared, and there are no other numbers in the entire universe that are both positive, and when you raise them to a power, their difference is 1. Kind of cool. It's kind of wild. Technically, you could say 0 and 1, but 0 is not. Like, yeah, it's an interesting math fact there for you. So then we can figure out what's going on here. We can rewrite this as 1/3 the integral from 1 to 9 of u to the 1/2 du. We anti-differentiate. We get 1/3 times u to the 3/2 times 2/3 from 1 to 9. We rewrite that as 2/9 times 9 to the 3/2 minus 1 to the 3/2. And we do simplify it here because we can. 9 to the 3/2 is the square root of 9 cubed, which is 3 cubed, which is 27. 1 to any power is 1. So we end up getting 26 times 2/9, which is 52 over 9. Yeah, okay, so Additional question. What is the average value of f of x equal to x squared times the square root of x cubed plus 1 on the interval from 0 to 2? What does average value even mean? Well, the meaning is probably harder to describe than the actual way we calculate it. Because calculating average value is super straightforward. You find the integral on the interval and then divide that area by the length of your interval. So the answer is actually super easy. The average value of this is equal to, is going to be the integral from 0 to 2 of x squared times the square root of x cubed plus 1, which we just found to be 52/9, divided by the difference between your a and your b value. So calculating average value is super straightforward. It's just your area divided by your width of your interval. That's going to be 52/9 divided by 2, which is the same as 52/9 times 1/2, which is 26/9. What does this actually mean? Well, can I draw this thing? Yeah, I can probably draw this thing. Sure. So this function looks vaguely like, let's see, if you plug in 0, you get 0. If you plug in 2, you get 4 times the square root of 9, which is 4 times 2, which is 12. Sure, that seems not too terrible. And so this function probably does something wild like this. Like that. So imagine you have, I used to say, anyone know what an ant farm is? Okay, people know it. Okay, so imagine you have an ant farm. This is your ant farm, and it's got a real high wall, height 12, and you poured in the weird white, not quite sand stuff, little rocks, whatever they are, and they came in like that. Not very like equally distributed. So then you decide to shake it up so that everything is at an even level. And that even level, that even height, that average value, that is the average value, where you've got the same amount of area, but it's equally distributed across the same height. That's the average height of the function, also called the average value function. So the average value here is the value where, and that, let's see, my average value here is 26/9, which is a little bit less than 3. Maybe it looks like about like that. So there's my average value, where this red area is the same as this blue area. So it's where all the area would level. But the way you can find that is by taking your total area and then dividing by your length to get the height, because base times height equals area. So the idea of average value actually isn't that terrible to contemplate. You're just taking the total area dividing by the length to get the average height, or the height you would get whereas if you leveled everything out, you would get that height. So it's not hard to calculate. So I want you all to try this one. To find the average value of, what do I got here? Sure. F of x equal to 3x squared plus 4x plus 1 on the interval from -1 to 3. So try to do that. Find the area and then divide by something. I think you know what.
So I know that's probably not enough time to do the problem, but looking at the clock, and be like, there's still a couple of things I'd like to say. So let's go ahead and do this. It's not terrible. We're going to anti-differentiate this. We're going to get x cubed plus 4x squared over 2 plus x from -1 to 3. All that divided by 3 plus 1, which is 4. That ends up being, plugging in 3, we get 27 plus 2 times 3 squared is 18 plus 3 minus plugging in -1, we get -1 plus 2 plus -1. That all adds up to 0, which is nice. All that divided by 4, I know it looks kind of terrible. So then we get 27 plus 18 plus 3, which is going to be 48 divided by 4, which happens to be 12. So the average height of this function on that interval is, yeah, we shouldn't, I will couple more things, just some things that are occurring to me as I'm thinking here. What if we wanted to find the integral from, 0 to 6 of x squared, sorry, let me see, minus 6x plus 5 in absolute value? Seems like a terrible question. And it is kind of a terrible question because unlike maybe other absolute value questions we've encountered, this one you can't just do graphically. Here's what I mean. We'll come back to this one. So if I said something like find the integral from 0 to 6 of the absolute value of x minus 2, we could just draw that. Say, well, the absolute value of x minus 2 looks like a V shape. The bottom of the V is at 2. It's kind of this thing. And then the area is going to be that's a 6, not a 4. The area of this triangle plus the area of this triangle. This triangle has a base of 2, a height of also 2. This triangle has a base of 6 minus 2, and a height of also 2. I plug in 6, I do get 4. So this area is not too terrible to find. We can find this integral from 0 to 6 of the absolute value of x minus 2 by writing it as 1/2 base times height plus 1/2 base times height. So 1/2 times 2 times 2 plus 1/2 times 4 times 4 is equal to, I think, 10. 1/2 of 4 plus 16, which is 1/2 of 20, which is 10. So if you're asked to find the area under an absolute value of a linear function, usually we do it just by drawing it and finding the area. But if you have the absolute value from that's nonlinear, like this parabola here, it's a little bit worse. Let's draw it. So y equal to x squared minus 6x plus 5 is an upward opening parabola, and it factors as x minus 5 times x minus 1. So I know it looks something like this. It's got x-intercepts at 1 and 5. Which means its vertex is between, is this, if you split the difference between 1 and 5, you get 3. The vertex is at 3 comma something. I don't really actually care about the y value. And so it looks kind of like this. So then if I want to find the absolute value of that function, what I do is I take the part that's negative and I flip it up over the x-axis. So check this out. I know it's kind of weird, but if you actually wanted to graph the absolute value of any function, you can just take the negative parts and reflect them across the x-axis. So if I was graphing y equal to the absolute value of x squared minus 6x plus 5, I'm going to do the same graph, except now this part still looks like it does. It still looks kind of like that. And this part here still looks like it does over here. But then the middle part, instead of going down like that, it's going to go up like that. Kind of funky. What that means is we can break this up into finding this area, and this area. So these two parts, the function's still as it was, but this middle part, you're gonna have to do the negative of the function to give you positive values. So what we're gonna do is we're gonna break up our integral here. We're going to break it up into three separate parts. The integral from 0 to 1 of the absolute value of x squared minus 6x plus 5, plus the integral from 1 to 5 of the absolute value of x squared minus 6x plus 5, plus the integral from 5 to 6 of the absolute value of x squared minus 6x plus 5 dx. I will point out that x squared minus, sorry, let me move over here now. The x squared minus 6x plus 5, which is equal to x minus 5 times x minus 1, is going to be negative if x is between 1 and 5. If it helps, we can do a little number line thing. Say, here's 1, here's 5. Pick a number be larger than 5, like 6. 6 minus 5 is positive, 6 minus 1 is positive, the product is positive. Pick something, I mean, we also saw the graph, right? You look at the graph, we saw the graph, the function certainly was negative between 1 and 5. But also, you can do this number line thing. Pick a number between 1 and 5, like 2. 2 minus 5 is negative, 2 minus 1 is positive. And then over here, it's going to be positive. Which means that to rewrite this integral, the parts where it's already positive, the absolute value is not necessary. So we can write this as the integral from 0 to 1 of just x squared minus 6x plus 5. But here, between 1 and 5, where the insides are negative, to change that negative number into a positive number, we multiply it by -1. So we're going to get -1 times x squared minus 6x plus 5. And then finally, this last part is from 5 to 6, well, if we're bigger than 5, the function is positive, so we no longer need the absolute value. So that's how we can deal with the absolute value of a more complicated than a linear function. We break it up into the parts where it's positive and negative, and then whatever negative parts we have, we flip over or we multiply by -1 to make them positive. And then we can do kind of a lot of terrible integrating. We're going to get x cubed over 3 minus 6x squared over 2, which is 3x squared, plus 5x from 0 to 1. I will point out that this part's just going to be the negative of that. So instead of thinking it through, I'm just going to say I'm going to get plus negative x cubed over 3 plus 3x squared minus 5x evaluated from 1 to 5 plus, I guess I put the parentheses around this too, x cubed over 3 minus 6x squared over 2 plus 5x evaluated from 5 to 6. And then we could plug all those things in, which would be kind of awful, but I think we can see what would happen here, right? We're going to get 1/3 minus 3 plus 5 minus 0 plus 0 plus, and then it's going to be awful, minus 5 cubed over 3 plus 3 times 5 squared minus 5 times 5 minus, then you plug in 1 and you get -1/3 plus 3 minus 5. And then finally you plug in 6 and 5. 6 cubed is 216 divided by 3 minus 3 times 6 squared plus 5 times 6 minus, then you plug in 5 and you get 125 over 3 minus 3 times 25 plus 5 times 5. So the last part there, not really the point. The point more is that if you have an absolute value of something like this, you can in fact deal with it by breaking it up into the parts where it's positive and the parts where it's negative, and then changing the sign of the parts that are negative. Yeah, it's kind of a little bit terrible. Next class, we will start talking about finding the area between curves.